Welcome. In today's video, we are going to derive an expression for the mean and variance of a hypergeometric distribution. To begin with, let us define the probability mass function. So suppose that x is distributed with a hypergeometric distribution with parameters, we'll say n, which is our large population we're selecting from, d, the number of defectives that we're trying to select, and subscript n, the number or the total number of objects we are selecting from the big population. The PMF, or the probability mass function of x, is given by the following. Px of x is equal to d choose x, which is basically the number of ways of selecting x from the defectives, n minus d n minus x, that's saying whatever's left over you're choosing, n minus x, how many ways can you select that from the non-defective population? And of course the final step there is to recognize that we're selecting n choose n. How many ways can you select small n from the population of big N? And of course this this PMF only exists for the following values of x. Take max of 0 of n plus d minus n, and then we go all the way up to the minimum of n and d. And these generalized, this generalized sample space of x is just to ensure that, for example, you're not selecting negative values, hence why there's the max that we have here, to make sure we're not selecting negative values from the sample space. So, let us first begin with the expectation. So, unlike in other videos, I am not going to derive simply an expression for the expectation. Instead, I'm going to derive an expression for the following. The expected value of the random variable x choose k. Now, I promise you that this expression here eventually is going to allow us to calculate the expected value of x, but it's also going to allow us to calculate the variance of x and the second moment of x with some ease. Now, it will be a bit more computational and a bit more algebraic, but I assure you that in doing it this way, we get a comprehensive view of the expectation and variance in a more efficient manner, let's say. So without further ado, let's begin. Let's first evaluate this using our definition of expectation of a discrete random variable. So that's the sum across the support of x of the function, which is x choose k, multiplied by the probability mass function at x. Next step, for the remainder of this, I'm just going to write the summation across x, an element of the sample space. The reason being is because I don't want to write these big expressions as the terminals of the summation. For now, I'm a little bit lazy, if that's what you want to call me, but for now, just remember that you are going from this terminal to this terminal throughout the video. So, we've got x, choose k, multiplied by, now we can stick in our probability mass function, d choose x, n minus d, n minus x, all over n choose n. from this point, what I'm going to do is I'm going to expand the definition of the first two terms. The reason I'm going to do that is because by those expansions of the combinatorial factor, I can actually see that there's going to be an x factorial here in the numerator here and an x factor on the denominator in this expansion. So I'm hoping they're going to cancel out as sort of my first point of reference. So that's x isn't an element in the support of x factorial over k factorial x minus k factorial times d factorial on x factorial d minus x factorial. That's this term that I've just expanded by the definition there, times, and then of course we still have the n minus d n minus x expression, and of course we still have our n choose n down the bottom, and I'm just going to put that summation sign here. And what do you know? Here you have it, that x factorial cancels with that x factorial here, and we're left with an interesting expression. Now, I'm going to just sort of pause here and notice that we've got a d factorial over a k factorial. Now, I'm going to artificially insert a d minus k factorial down the bottom. The reason I'm doing that is because when I combine those two expressions and the d minus k factorial, I'm going to get a combinatorial expression again. And I'll show you what I mean in a sec, in case the written language wasn't that clear, or the verbalization of what I'm trying to arrive at is I'm saying if I put a d factorial, I've got a k factorial, and then I've got a d minus k factorial. So I've artificially inserted myself there. Then I have to multiply the numerator by a d minus k factorial, so theoretically they cancel out. And then, of course, I'm left with, down the bottom here, we've still got our x minus k factorial and our d minus x factorial here. So x minus k factorial, d minus x factorial, and then we've still got our n minus d, n minus x, close that bracket off, all over n choose n. And what we can notice here is that this expression here now is what I'm getting at. Looks like a combinatorial expression. In fact, it is by definition equal to d choose k. Now, the other thing to note is that this d choose k is independent of the index of the summation, the x, so we can actually bring it outside the front of the summation, which is why I've put it here for now. And we still have our d minus k, x minus k factorial, except I'm going to rewrite this d minus x a little bit strategically here. Instead, what I notice is I've got a d minus k factorial and an x minus k factorial. If I had d minus k and then a x minus k factorial, then I have another similar combinatorial expression here, right? Where I've got term 1, term 2, term 1 minus term 2. Hey, what do you know? This d minus k and then minus x minus k actually gets us back to d minus x factorial. When the negative k here will cancel with the minus negative k here, just leaving us back with d minus x. So we haven't had to insert anything artificially here. I now have an expression. And then of course, I've still got we've still got our n minus d, n minus x, all over n choose n. And at this point, you might be saying, well, this is looking a little complicated, but I can assure you we're going to get somewhere in the next step. So we've got d choose k still at the front. We've got our summation, x is an element of the support of x. Now this expression here, while complicated, is actually just a combinatorial expression. It's d minus k choose x minus k by definition of the factorial. This expression here is a funny one, and I'm just going to rewrite this strategic, or in a sort of cheeky way. I'm going to rewrite this as n minus k minus d minus k, and then n minus k minus x minus k. And this turns out to be exactly the same expression, because when you expand these brackets out, the minus k and the minus negative k cancel out, giving you back the n minus d. Similar with the bottom expression, you get back to n minus x. And although this may look complicated, I assure you there's a reason, or there's a method to the madness here. But for now, let's continue onwards. But to give you a flavor of why this is the case, it's again because ultimately what we're trying to do, I'm trying to make this expression inside the summation look like a probability mass function. That's really what my end goal is in all of these manipulations and algebraic manipulations. My end goal is that. And the reason why I strategically try to have these minus k's everywhere is because I noticed that I have an x minus k here. So if I do a slight change of variable later on, where I have y is equal to x minus k, which I will do, what I'm hoping is it's going to look like a PMF of another hypergeometric distribution. That's sort of just to give you the reasoning as to why I'm maybe randomly at times just pulling things out of random. But that's sort of why my reasoning. So let's continue. And in the same sort of reasoning, let's have a look at that n on n factorial. N choose n at the bottom here. Now ideally we're going to have, well let's expand it first. N factorial on n factorial n minus n factorial. Kind of sounds funny to say, but it is lowercase n and uppercase n. I should really be a little bit more clear. Similarly, in a similar vein to what I was describing before, let me just copy and paste this expression here. Copy, paste the expression. Now, except let me just remove the bottom part for a second. So, as before, as I was saying, I want to make this look like a hypergeometric distribution. And you'll notice there is elements of the hypergeometric distribution here. Here, for example, you have an n minus k. In the original PMF, you just have an n. Similarly, therefore we sort of want a n minus k down the bottom, right? If we're going to try and make it look like a PMF, we want an n minus k down the bottom, or an n minus k factorial down the bottom. So that's what we're going to do. I'm going to artificially insert an n minus k factorial. I'm going to artificially insert, in fact, similarly, in a similar vein, there's an n minus k here where there is usually an n. So instead of an n down the bottom here, I also want an n minus k. So again, I'm going to artificially insert an n minus k factorial here. And then I'm going to have an n minus k minus n minus k. Again, I'm artificially inserting things into the fraction down the bottom here. But now I've actually got to sort of reverse them out. So that becomes n minus k factorial, n minus k factorial. The reason I'm reversing them out, all I'm doing is I'm taking the reciprocal of the two terms we've inserted. And you might be saying, well, why haven't you taken the reciprocal of the very final term here? And the reason I haven't taken the reciprocal of the very final term is because if you actually have a look, the negative k here cancels with the minus negative k here, and we're left back with the expression n minus little n, which is the same expression that we had before. So I don't have to cancel that. The only thing I do have to still include here is the subscript n, the little n and the big N that I had before. So I'm going to put those in factorial, n factorial. All right, now I think we're cooking. Now I think we're about to unravel this mystery of what this expression becomes. Because let us, now that I'm not feeling as lazy as I was before, first before I'm not feeling lazy, what I was going to say is I was going to change the terminals or put them through. But the first thing to notice actually is that this expression here is independent of the index x of the summation sign. So these expressions all the way around here can come outside the front. In fact, the ones down the bottom could also come outside the front because they're independent of x, but I want to keep them here to look like the PMF. So these ones are going to come out the front. So it's d choose k. 1 over n factorial, close the bracket, n minus k factorial over n minus k factorial times, in this particular instance, we've got our expression. Now I'm going to put in our terminals of x is equal to, and if you recall what they were, max 0 n minus d plus blah, blah, blah. So that's what I'm going to write here. It becomes max 0, what did we say expression was? N plus d minus n, all the way to the minimum of n comma d. And then we have our expression here that I'm just going to copy across. Copy, paste that expression. I don't have enough room, but that's okay because this final term here down the bottom, I'm actually going to rewrite as simply, so we've taken out this factor here, this final term here I'm just going to rewrite as n minus k, choose n minus k down the bottom. And now we're really looking like a hypergeometric distribution. The only thing that we need to do here is let y is equal to x minus k, then what you get in your expression is the expected value of x, choose k, is equal to, we've still got our expression at the front here. I'm going to flip the fraction, so it's d choose k n factorial, n factorial n minus, well, actually, I'm going to write it a little bit differently. I'm going to write it in a way that we might be able to see. I'm going to write it as n factorial, or in a more familiar fashion, n factorial over n minus k factorial over n factorial over n minus k factorial. And you'll see I'm sort of beginning to see the formation of more combinatorial factors. Now, the summation sign here at the front, this is why I just define this variable x is equal to y minus k. So when x is originally the maximum of 0, and then n plus d minus n, that becomes the new terminal, actually becomes y is equal to the maximum of 0, n plus d minus n minus k. Then it has a minimum now value of n minus k d minus k. And of course our expression here that we wrote before becomes d, or d minus k, choose y, close the brackets, n minus k minus d minus k over n minus k minus y, all over n minus k down the bottom here. And if we really think about it here, we now have exactly a probability mass function of a hypergeometric distribution, just a new random variable. It doesn't have parameter dn and little n, it has parameters d minus k, n minus k, and little n minus k. So we can rewrite this whole expression, let me take this whole expression, copy it, paste the expression. We can rewrite this as is equal to. The first thing to note is I'm going to strategically put in a k factorial and a k factorial as part of the two fractions. The reason I'm doing that is because by putting it on both the numerator and the denominator of the fraction, they cancel out, but also now these look like combinatorial factors. The second part to recognize is that this component here I can simply write as, instead of the huge summation sign, I can write it as the sum of y is an element in the support of a probability mass function, where that probability mass function has a hypergeometric distribution with parameters, and I'll put it down here. The parameters are n minus k, n minus k, and of course d minus k as your parameters. So, keeping that in mind, we know by definition that the summation across a whole PMF of x has to be equal to 1 by definition of a probability mass function. So then this whole expression here just collapses to 1, and we're left with this final expression, which I will rewrite as d choose k, n choose k, and finally all over n choose k. Again, because those are the definition of the combinatorial factor. Now, I promise you that's where the hard algebra stops. After this huge derivation, it's going to become very easy to actually calculate the variance. Well, I say easy, but there'll be a bit more algebraic manipulation, but we're going to get there. So, now what we can note is the following cases. So, when k is equal to 1, what do we have? Well, our formula for the expected value of x choose k, well, that's just the expected value of x choose 1. Now, x choose 1, how many ways can you choose x? Well, you can choose it x times if you think about it logically. But if we want to do a more algebraic or rigorous proof of that, we can say that is x factorial over 1 factorial times x minus 1 factorial, close the bracket, by definition of the combinatorial factor. The top part of that expression can be rewritten as x times x minus 1 factorial. The bottom part of that expression just becomes 1 times x minus 1 factorial, and of course the x minus 1 factorial and the x minus 1 factorial cancel. We're just left with x over 1, which we simply stated as before was just equal to x. You can choose x. You can choose one object from x objects x ways. Now, therefore, we can now plug in our definition. We can say that the expected value of x is equal to the expected value of x choose 1. Now we can use our definition that we came above. D choose 1, this expression up here, by the way, that I have, that becomes D choose 1, N choose 1, all over N choose 1. And quite nicely, would you have a look at that? How many ways can you choose one object from D? Well, that's D ways. How many ways can you choose an object or one object from N? N ways. And finally, how many ways can you choose one object from big N? Simply equal to N ways. So after all of that, we can usually rewrite this as N times D on N. In other words, it's the number of samples that you take from the entire population times D over N, which is the proportion of the defective samples. And intuitively, that sort of makes sense there. Now, we can do a similar sort of approach for the expected value or the variance. But first, to find the variance, we're going to have to find the expected value of x squared. To find the expected value of x squared, we're actually going to use what happens when k equals 2. So when k equals 2, we have the following. We have the expected value of x, choose k, is equal to the expected value of x, choose 2, which is the expected value of, we can write it here, using the definition, x factorial on 2 factorial x minus 2 factorial. Put that on the line, which by definition we can rewrite as the expected value. Now x factorial at the top here can be rewritten as x minus 1, x minus 2 factorial. 2 factorial can just be written as 2, and we've still got our x minus 2 factorial down the denominator. And of course, the x minus 2 and the x minus 2 cancel. And because the denominator here, 2, or you could think of it as a factor of a half, is independent of x, we can actually bring it outside the summation. So doing that, we can rewrite this as a half expected value of x minus 1. Or alternatively, we can find, we can actually say that the expected value of x minus 1 is equal to 2 times the expected value of x, choose 2, just rearranging the equation that we have here. So, noting that to find, say, the expected value of x, or the expected value of the second moment, we know from previous videos that this expression here is what we typically use to evaluate the expected value of x squared. So let's do that now, and the reason for that, in case you haven't seen the other videos, is if you were to, say, expand these brackets here, or if I were to prove this, we note that the right hand side, if you were to start with it, the expected value of x minus 1 plus the expected value of x. The first thing we'd do is we'd expand the first expression, so that becomes the expected value of x squared minus x, if you expand the brackets, plus the expected value of x. We also know by the rules or the properties of expectation that the expectation of a difference of random variables is the equivalent of taking the expectation of the random variables individually and subtracting them from one another. And then, of course, we notice that the minus x and the plus x expected value of x cancel, which therefore leaves us with the expected value of x squared. And of course, we've proven that that is equal to the left-hand side. So, noting all of that, we can now start calculating, or to calculate the expected value of x squared, we'll calculate the expected value of x times x minus 1, which we also have an expression for above here, using the combinatorial factor. So let us begin. The expected value of x minus 1 is equal to 2 expected value of x, choose 2, which is equal to, in this particular instance, 2 times. Let's use the formula that we developed a second ago. This was the formula for a generic k. So let's substitute in a value of, let's take that generic formula that we had for the expected value of x, choose k. We will put in a value of 2 in here. Oops, 2, apologies, 2, 2, 2, 2. We know from previous experience when we derived an expression for some variable, choose k, we ended up with this expression here, a half x minus 1. So in general, this expression here becomes a half d minus 1 times a half n minus 1 all over a half n minus 1. And that's only because I don't want to continually derive the same expression, but we know from previous experience that's what we get. So we note that this half here down the bottom can cancel with this half. This 2 here can cancel with this 2. And so now finally here we're left with d, or I should say nd, d minus 1, n minus 1 in the top or in the numerator, and then n minus 1 in the denominator. So far, so good. Now we can calculate, or we can have an expression for the expected value of x squared. So the expected value of x squared, as we discussed above, is equal to the expected value of x minus 1 plus the expected value of x. We know that the first part of this expression is this term here. Copy that down, accidentally copied one of the yellow parts, plus we know our expected value of x was nd on capital N. So now we're going to just work out or derive some simplifications here. The first point of reference I note is I want to find, when we're adding fractions, we want to find the lowest common multiple between the two denominators of the fractions we are adding. In this case, the lowest common multiple will just be n times n minus 1. So the first expression doesn't change. D minus 1, n minus 1, all over n minus 1 plus. However, we do need an n minus 1 in the denominator on the second fraction. To get there, of course, we had n. We have to go from n to n minus 1. That's multiplying by n minus 1. So then that becomes n d n minus 1 here. Now what we can do here as part of this expansion is I notice there's a common factor of n minus d and n times d. So I can take that out as a common factor, which leaves me with d minus 1, n minus 1 plus n minus 1 all over n minus 1. And after a bit of algebraic manipulation, we can say that's n d. I'm going to expand the brackets here that I have, and I'm simply going to rewrite that expression as d, not d, but dn minus d minus n plus 1 plus n minus 1 all over n minus 1. And we'll notice that the plus 1 and the minus 1 here in the expansion will cancel out. And so we are left with, in this particular instance, nd. I'm just going to rewrite it as minus d minus n plus n all over n minus 1. we're almost at the finish line here. The final part is, of course, to derive an expression for the variance of x as promised. And the variance of x is, by definition, the expected value of x squared minus the expected value of x all squared, which ends up giving, so we'll just take this expression at the top, copy that down, paste that expression in, and then we're going to subtract n d on n, which is the expected value of x all squared. This then becomes, in the next step, we can take the fraction here. We're going to just paste it in for now. I'm just going to rewrite this as n squared d squared on n squared. Notice we need to now find a lowest common multiple of n squared and n minus d when we're adding fractions. The lowest common multiple of those two quite simply happens to be n squared n minus 1. So to get to that expression for the first fraction, we needed to multiply the denominator by simply n. So I'm going to multiply the numerator n d capital N d minus n plus n. I've multiplied there the numerator by n. Similarly, to get from, or the second fraction, right, will be, again, n squared on n minus 1. To get that expression down the bottom, I had to multiply the denominator of the second fraction by n minus 1. So I need to multiply the top fraction, or the numerator, by n minus 1. Alright, now we're getting somewhere. Slowly. What I will do is I will expand this top fraction here. So when I expand this top fraction here, I get n dn times nd. That gives me n squared d squared n minus, then for the second term here, I'm going to get n dn times d. That gives me n d squared n. The next term is that three-factor expression times n. That gives me minus n squared dn. And finally, the final term times the final term just gives me plus n d capital N squared. And we're subtracting this expression here. I'm just going to expand it out. That gives me minus n squared d squared n plus, the reason it's a plus is because it's minus the negative here, plus n squared d squared, and I'm going to put that all over a fraction n squared n minus 1. And something brilliant happens here, because this n squared d squared n cancels with this negative n squared d squared n, and so now I can pull all the terms together, or give us what's left over. So it's negative, well, I'll put the positive terms first, n dn squared plus n squared d squared. Those are the two positive terms at the back. And then we've got minus n d squared n minus n squared dn all over our expression here, n squared n minus 1. We're going to do a little bit more algebraic simplifying or algebraic simplification here. And actually, I noticed that all the top, the numerator has a common factor of n and, or little n and d. So I'm going to take that out as the common factor, nd. Then we're left with n squared plus nd minus what would be d big N minus what would be n, appears to be n at the back. Close that bracket off, and we've got n squared n minus 1. And finally, I think we can do one last bit of simplification here, because this expression at the top can be factorized to n minus d, close the bracket, n minus little n, all over n squared n minus 1, or quite simply, put in another way, which is common, is to rewrite this as n d over n minus d over n, and then whatever's left over, n minus n on n minus 1. And this, ladies and gentlemen, is the expression for the variance. And if we want to go one more step for completeness, the standard deviation, which is the square root of the variance of x, we can just simply say that is the square root of the expression that we've just derived. Copy that down, paste it here, and then finally close off the top part of the square root sign. So there you have it, ladies and gentlemen. We have derived the variance and mean of the hypergeometric distribution. We have relied on the expected value of x choose k, the generic case. Then, after some lengthy algebraic manipulation, we have been able to get to choose a value when k equals 1 to get the expected value of x, and then using when k equals 2, we were able to do some rearranging of some equations and some algebraic simplification. After a long, lengthy, rigorous process, we've now come to an expression for the variance and the standard deviation. I hope that video was useful. I hope to see you in the next one.